Okay. We can do that. We can extend the due date. Okay. One of the things that I want to do with this is I realize I want to make sure that it's as interactive and as discussion based as possible. Which what I'd really like is for the rest of the course participants, the rest of the students to be here live if possible. So if you're watching this on the recording later, I invite you to come back, to come to the live lecture if you can. All right. But so like I've noticed that in the previous couple of videos, I've really kind of focused heavily on the slides. And so I don't want to do that too much. I don't want to focus too heavily on the slides. I do want to be able to discuss them. So my plan is, what we will do going forward is I will have the slides for the Friday available on, I'll have them uploaded to the formatted and the text corrected and all that stuff, uploaded to the class materials folder no later than Monday of that week. And so you guys can look them over. And what we'll do, instead of me just kind of going through them and saying this is what this slide means and this is what this slide means and stuff like that, what we'll do instead is we'll discuss stuff. What did you read out of those slides, and what did you understand, and what were you confused about, and stuff like that. So because I didn't get the slides up in time this week to be able to do things that way, we will go ahead and just kind of roll through, and I'll focus on some of the key slides that I want to make sure I speak on, but we will spend hopefully the majority of this time just kind of in some discussion with each other. Okay, so let me go ahead and share some of this. Let me share so the clean room, this isn't going to be the focus of today's, because I really want to spend more time discussing the next set of slides, what's labeled the Lecture 5 set of slides, because that's the software quality assurance slides, kind of the software quality assurance overview. But there are some things in here that, as I was going through them, I said, no, I really don't want to just skip this. And I wouldn't have just skipped it. I would have given these to you and let you have them as material to read through. But I don't want to just do that here. Okay. So we won't go through too much of this, but basically the idea is about changing out the idea of how we used to develop software, which was in a lot of ways a lot of ad hoc stuff, but really kind of more rigorous engineering-based practices. So really kind of applying a process to how to develop software. Because again, and I mean, I've said this before, and I'll say this probably more times than we can count in the next few weeks that we're here together, there really has been too much of a focus in the past on code writing being the main thing that software development is about. And yeah, it's kind of where the material is made, and and the truth is, in just about anything, we do, building buildings, for example, or laying down pavement for roads, or there's actually been here outside my home for the past few weeks, there's been a lot of digging up of the road to lay down electrical cables, to put the electrical cables underground, and we kind of look at the action of doing that, of digging up the road, laying the cables, of building the building, of writing the code as being the thing that we have to do, the thing that is like the focus of what we're trying to produce. But the truth is that before they dug up any bit of road, before they laid a single brick for the building that I'm sitting in right now, they had to do a lot of planning first, right? And before they let anybody move into this building, have inspectors come and make sure that the building was, good and was ready for people to move into, right? They didn't just finish the building and assume, okay, everything's done. We don't need to test anything. We don't need to check anything. We just assume it's good and we move on. No, they had to have testing of the building to make sure that it was good, right? So basically, kind of some of the aspects of software engineering software process development is all about applying that same idea of we're not just going to focus solely on we're not just going to focus solely on the code writing as being what software development is about, but all the other aspects of it as well, planning and testing, stuff like that. Okay, so basically you have kind of this process. You have some tasks, some components that we need to have. The specification, which would be kind of in a sense the requirements, but it's also design as part of that. The development, the correctness verification, independent product testing. Now this would be, so again, a lot of times as developers, we don't like doing testing, so we end up not doing a lot of it. Whereas if we have someone who's separate from us be able to do that testing, whether it be an in-house quality assurance department, or oftentimes if we have a good customer, what they will do is they will have their own testing that they will do as well before they accept our product. So what's really good is when you have a situation where both the software development company and the customer both do their own rigorous amounts of testing to make sure it is correct, that as far as they can tell there are no defects, and then the customer can, then both the customer accepts with confidence and we also deploy with confidence. Okay. Reliability and process control as well. But one of the things that is cool about the clean room activities is you can have these teams that will exist and work concurrently. So again, we showed earlier, I think down here, the same slide is, where is it? It was down here, is it? Oh, it's on the next set of slides actually. The whole waterfall process that I talked about last week. So the idea was that you test only after all the coding is done. But if we look at this idea of doing things concurrently, you can have where both the planning of development, but then also the code writing, the construction over here can be done concurrently at the same time as the test cases are being made. So if you have your you have a quality assurance department, or even just developers that their job is to write test cases, then what we can do is we can be writing code at the same time that tests are being developed. And so as the code gets complete, it can also be tested, and then, then save some time that way. That way we don't have to have code, we don't have to have developers over here that are just kind of waiting for the results of their tests after they're done writing. Because what could happen is that if we just have this single straight line process where coding comes, then testing comes, well, what happens if an error is found in testing? We've got to send it back to the developers for them to be able to correct the problems. Well, a lot of times, either that requires the developers be sitting around waiting for their code to be tested, or what happens more often is the developers have moved on to some other task, that now that task has to be interrupted in order for them to fix the problem that was found in testing. So yeah, so in this case, if the tests are generated at the same time that the coding is being done, then we kind of do those things concurrently and make it a little bit more efficient. All right, let's see. So we did talk a little about this incremental idea where you have like pieces of the system kind of development, some increments. If you've ever heard of the Scrum process, I think we talked about that last week. That would be a form of incremental build, and so you kind of do some of it. Then once that's complete, you move on and you move on, and kind of the testing can be done incrementally as well. Now, notice that in each of these, so you have this increment 1 for development, increment 2 for development, increment 3 for development. But in the testing, you can test increment 1 once it's done, but once increment 2 is done, you have to test both of them together. And the reason for that is, I'm sure those of you who have had internships or have worked in the field have seen this before. What happens if something about increment 2 makes something in increment 1 stop working? If we don't test if we don't make sure that increment 1 is still working well, then we can end up with unknown defects that go out into the field. Yeah. Let's see. I do want to go ahead and focus on this, the idea, because this will come back up in the next set of slides as well, as the idea of, do you know black box and white box testing? Do you know those terms? Black box testing, white box testing?
No, actually, I did not heard it.
Okay. That's actually, it doesn't surprise me actually, because when we don't talk about, again, don't give a whole lot of information to developers about testing. So the idea is the black box testing means that we really can't see inside of the unit. So like, for example, if I wanted to test, I think all of you, I would imagine all of you know Java. So if one of you doesn't, you'll need to let me know that, because one thing I'm going to talk about today, I'd like you to start working on in regards to Java. So for Java, there's certain methods that exist in classes that we use, like the absolute value method in the math class, a lot of string methods like string length and stuff like that. So the thing is we don't know what's inside of those methods. Right, we can't look into the Java code. Now, we might be able to have access to it if we did some Google searching and we looked on Oracle's website and stuff like that. But for the most part, those methods, we know if we put something in and then it returns a value, we know it works, right? But we don't know about what's inside of it. So that's what black box testing would be. So you give a tester, if you're a developer, you give a tester, or you give the customer this method or some other component that they don't get to see inside of it. They just know they put in values and they expect certain values out. Okay, black box testing is what most is probably one of the more I want to say one of the better forms of testing, but it's not really so much better. It's just that when you don't know what's inside, sometimes you don't know what inputs are acceptable, and so you can actually get a better test. That I may have to tell this story because it just shows such a clear view of how developers see the world versus how customers might see the world. And so again, one thing that I've told you guys before is my first job in the software field was actually not as a software developer, but was actually as a quality assurance specialist for a very small company. And there was one time that there was a search page that I was testing. The developer had finished the search page for different documents in our system, in our database. And one of the fields that you could search based on was a currency amount. So if the document represented, like it had a dollar amount associated with it. And you could search for all documents that were greater than a minimum number of dollars and less than a maximum. So you could put, you could say $100 in the minimum field, and you could leave the other one blank, and it would just give you all documents that were $100 or greater. Okay, that was what it was supposed to do. So the way that the page was set up as a web page, it was a .NET application. Was the developer had put a $sign on the page, and then next to that was a text field. Okay, now that text field expected a numerical value, but me, trying to be a good tester, I typed in another $sign. So I typed in, $100 or something, and I clicked OK, and it gave me this big Oracle database error. If you've ever seen them, it's like a big yellow bar at the top with some text inside, and big server error. And so I did what I was supposed to do, which was I issued a bug report and put that into our bug tracking system. And I mean, as soon as I hit submit, I mean, just within a few minutes, the developer's over at my desk telling me, I don't understand. What's your error? What's going on? And I showed him what I did, and I showed him what the error was. And he said, well, the problem is you put a $sign in there. It's supposed to be a numerical field. I said, well, yeah, but we should check for that, because what if the user puts in something not a number? Oh, no user's ever going to do that. Well, you know, truth was, I had worked as a help desk, as a tech support for the university I had gone to just a few years prior to that, and I was like, I told him, nah, users can do some silly stuff, man. So basically, black box testing is where we don't know anything about how it works inside. So what he was doing was now clear box is another way to phrase white box. He was doing what was white box testing. When he submitted that to me, he said it works according to everything that I've done to test my search page. And what he had done was he had only tested it with inputs that were numeric. Okay, and the reason he did that was because he knew that field needed to be a numeric field, but he hadn't put any restrictions on it. He hadn't done anything like that. And so basically what we ended up doing, after that was he changed the field because, basically he finally gave in and said, okay, I could see how somebody might do something that's not numeric. Is we basically had what's it called? Input validation as part of the field from then on, where basically if they put anything non-numeric in there, instead of giving them a server error, what would happen is it would come back with a message saying, hey, this isn't a correct entry over here. Okay, so that's black box testing. Again, white box testing is just kind of the exact opposite, is that we do know what's inside. We know not only what inputs should generate what outputs, but we also know what's kind of inside of that box. Like, how is it done? Is it done through a loop, an if statement, stuff like that, so that we can have a better idea of what inputs might crash the system or might be a problem. Okay, and then state box is kind of an in-between. It's where we know some of the inside, we have an idea of what the state is, but really we don't know fully what's inside of the box. Okay, so if we look at it like this, again, black box, we have some input or stimulus might be another word, and we have some output or response. We don't know anything about what's inside of here. State box, okay, we have this black box inside, but we also know that a current state might do something to impact how the internal code is operating. I generally know that testing tends to default into either black box or white box, clear box. State box isn't used as much because if we're going to have where we don't really know what's going on in there, black box just tends to be understood as the best way to do it.
Actually, I did not understand the real difference between a state box and a black box. So,
okay,
isn't it just like the black box?
it's very similar. So the idea is that we have an understanding. So if we look back at the description here, kind of gives an intermediate view of the component, and we have an internal state representation and an internal black box. So we know that if based on especially for anything where it's the output is not just dependent on the input alone, but also on a current state. So what are they called? I'm trying to think of state machines, right? So if you have like a state machine where if you're in state, A, and you receive a certain input, you move to state B, or if you receive a different input, you move to state C instead. So if you've ever seen any of that where you have state machines, that's not just input this, get output that other thing, but you also have, depending on what state you're in,
now I get it.
Okay.
Thank you very much.
Sure. And then you can also have clear box where So I mean, I think this diagram from the text is a little bit misleading because it kind of shows two black boxes inside. Really, in true clear or white box testing, you kind of have a complete view of inside of everything inside, so you just kind of know what's going on throughout. I mean, I guess in one sense, if sometime in the Java code you use the absolute value method or like a string method or something, that counts as a black box, true, but really in the grand scheme of things, you should know everything throughout. Let's see. All right, so I do want to talk a little bit about this because like this whole correctness verification idea is basically making sure that the code or the unit, if we're doing a unit test or something like that, that it does what it says it's going to do. All right. So if we were to say, let's say an example is the program is supposed to, if x is, if we give an x that's beginning as greater than or equal to 0, so that's a given initial condition. We have some value of x that's greater than or equal to 0. Okay? Now, the output of the functions in English should be that if x is odd, set x to 1. If x is even, we should set x to 0. Okay? Now, I'm sure that you guys are thinking over there, well, that's not the most efficient way to do that. Right? But is it correct? Will this set an odd value of x to 1? Will this set an even value of x to 0? Thoughts? Will it set an odd value of x, an odd non-negative value of x to 1, an even non-negative value of x to 0? Are you working it out for all possible values of x?
Actually, I'm not sure if I get it correctly.
Sure. So so the idea here is that we take a particular set of code and we want to know, will this do what it says it's supposed to do? So the idea is if we, so the idea is what we want to do is if a value of an integer we call it x. Starts out greater than or equal to 0, so a non-negative. What we want to do is we want to have a control structure that sets that if the value starts out odd, we want to make x 1. If the value starts out even, we want to make x 0. So then the question is, if this while loop down here that I've highlighted, does that do what this says up here?
No, because the x should be greater or equal to 1. I guess no, but for there's a problem with the 1 value. If the x is equal to 1, nothing's gonna happen.
Right, so if x is equal to 1, then the final value of x will be 1, right?
It's not even going to enter to the loop, so x will be nothing in that situation.
Right, so x starts out as 0, it won't enter the loop, it'll remain 0. If x starts out at 1, it won't enter the loop, it'll remain 1. If x is 2, it will enter the loop, it will become 0, then it will exit the loop, and it will be 0. If x is 3, it will enter the loop, it will become 1, and it will exit the loop, and then it'll be 1, right?
Yes.
So then for those odd values, x became 1. And for those even values, x became 0. So in a sense, what this could be part of a function or a unit that its job is to test for if a value is even or odd. Okay. Now, this is not the most efficient way to do this by any stretch, right? A while loop, because what happens if the value passed, if x is something like 1,000? Well, we're going to have to loop through this thing 500 times in order to get 0 at the very end, right? We definitely could have used some other functionality, some modulo operator or something, in order to get what we're looking for. But that's the thing, is correctness verification is not about efficiency. Correctness verification is about, does it do the job that it's supposed to do? And so for this, the answer is yes. This does what this is supposed to do. Okay. Now, that's the thing, is you want to define an intended function, all right? Then refine to a control structure with other sub-intended functions, and we keep doing that until we get small enough that we can compose, that we can make them, and then we put them all together. And we're verifying the correctness of each one. We find out what its program function is, what is it actually doing. So the intended function would be this. This would be the intended function up here. The program function would be this. Okay, and we just make sure that the program function actually does what the intended function is supposed to do. So we compare the program function to the intended function, and we make sure that it's correct. So then some other examples of how we might do some correctness verification. We have an intended function f. We say g and then h. Does g followed by h do f? If the answer is yes, then we have a correct program function. Some other things that you might do is if conditional, right? Whenever the condition is true, does g do f? And whenever the condition is false, and so therefore you have an if-else situation here. Same with a while loop. And this is the one of the harder ones, because is termination guaranteed? That can be a very hard question to answer, right? Because if termination is not guaranteed, how do we know? How do you test to make sure that something does not enter an infinite loop, right? Well, because what if it does? If it does enter an infinite loop, it'd be kind of hard to write a test case for that, right? Or to write some test code for that. Right? And so that's a tough question to answer right there, but it is a necessity. We have to be able to at least estimate that as a yes, right? And so it's kind of like, you guys remember recursive methods, recursive programming?
Yes.
One of the requirements of recursion is that the recursion eventually ends, that we have some base case and we always get down to it at some point, right? And so can we guarantee termination? It's a tough question to answer. Good. And so anyway, and whenever condition is true, does G followed by F do F? And whenever condition is false, does doing nothing finally give us F? Right. Okay. There will be a team review usually as part of that, just to make sure. All right. Okay. So this would be some type of language supported assertions. This is the one thing I wanted to kind of get into with you guys here today. One thing I want you to, if you don't already have experience with assertions and with JUnit test cases, I would like you to go ahead and read up on that and get that. Does everyone know Java and have a Java IDE that they're working with, or that they could work with? Like if I gave you an assignment for that, I'm not giving you an assignment today, but if I were to give you an assignment today in Java, would you be able to do it?
Yeah, actually, I'm not familiar with Java. In most, I program with C#, but I guess I can catch up.
Okay. Okay, so I can give you some links to some Java. What I'll do is I'll send you Alper. I'll send you the slides from my syllabus for CSE 101. It has some links to some Java IDEs that you can look into. And I guess I could also, I can send you an invite to the Google Classroom from last year's CSE 101 as well, and you can look through some of that.
Thank you. Actually, I used IntelliJ, and there was another one, but Eclipse.
Okay.
But only for a little, and it was like 5 years ago.
Okay. Well, what I would like you guys to all do, assuming that the other two, and anyone else, if anybody else is not able to attend the live lecture but is watching these later, what I would like you to do is become familiar with JUnit test cases, so that you can have an idea of how to write test code. You will have a test case assignment at some point this semester, so I would like you to go ahead and become familiar with writing JUnit test cases. Okay. So anyway, the idea though of the assertion is that when you assert, right, if this is true, it acts like don't do anything. There's no problem. Just keep going. If this first part, this conditional, if it's true, then we move on as if no problem. If it's false, then what happens is the assertion will generate an exception. So it's like becomes like a runtime error. Okay, so this whole assert statement is kind of the basis for JUnit test cases, for assert methods in JUnit test cases. So what happens is that if x is greater than or equal to 0, then we will generate an exception and we won't even do the rest of this. But if it is, then we just move on. Okay, so then we say, okay, the nx is whatever the value of x. Then we keep looping through as long as x is greater than 1, and we keep looping through, subtracting 2 off of x each time. So basically, even numbers become the next lower even number. Odd numbers become the next lower odd number. And we keep doing that as long as x is greater than 1. And once it's less than or equal to 1, then we pop out, and it is either 0 or 1. We print out outx, and then the reason why we do these printouts is more about testing than we wouldn't really want that inside of our method, right? So at the very end, if x is equal to 0 or x is equal to 1, then remember, if this is true, we don't do anything. If this is false, then we generate this exception and display this message. The nice thing about the assertions, with the way this is done, is that we can leave that code in for building and for deploying. And as long as we have assertions turned off for the final build, then that code can stay in there and it won't ever be seen. So what you do is if you turn assertions off, then even if this would have generated a problem, it won't. It'll just keep going. Okay. But the idea is that we include these in here for testing purposes. Okay. So that's about it with what I wanted to do with the clean room slides. Again, I want to go ahead and okay. What I want to do is now I do want to focus more on. I'll focus the rest of our time on this lecture 5 stuff. Okay. The idea of software quality assurance. Because we talked about this a little bit before, like what is software quality? We talked about, is there a way to guarantee 100% that software will work? And we kind of agreed, no, we can't. We can't do that. So what is software quality? I mean, how can we even test that? If we can't guarantee that software is going to work, how do we understand what is quality and what's not, right? And so the idea is that in the most simplistic way of putting it, quality is simply something that implies that the software does what it's supposed to do. Okay? A little too simple because that's not, for one thing, that's not quantitative. That's a more of a qualitative way of saying it because we can't measure that, right? We need something that's a little bit more quantitative for us to be able to measure how good software is. So maybe some attributes that we may want. There's a lot of attributes, right? We want efficiency. We want things to run fast. We want portability. We want them to be able to run on multiple types of devices. We definitely want security, especially if we're doing anything like financial or government related. We want reliability. We don't want things to crash in the middle of the day, or crash in the middle of the day would be even worse. All right, so understandability, we want our users to be able to know what they're using, right? And a whole host of other attributes here. And so talk about is that a lot of times you can have some of this more than others. And generally what our customers and what we have to do is decide what is most important and what is not as important. Okay. Let me get to software quality assurance activities. All right, so this is all types of activities that would be primarily associated with software quality assurance. One that you probably would say, yeah, I expected that, would be the testing of the software, right? So we have a series of test case, and the key to testing is being able to do it in a methodological, having a methodology, that's right. To being able to testing the software, not just saying, let me throw some inputs at this and see what comes out, but really having an idea of what specifically we need to test and where some of the boundary conditions are and some of that. Conducting formal technical reviews, so meeting with the staff, right, to be able to uncover some of those quality problems. Enforcing standards, so if there are standards that exist within your organization, or maybe legal standards, to make sure that they fall under that. The last thing you want is to have a piece of a working system that works really well, only to find out that something didn't conform to some legal code, and then therefore from then on, your software, you have to go back and like fix a bunch of problems from the legal standpoint. Right? We do want to be able to measure things and be able to track, right, and how changes, making sure that when we change something, it doesn't negatively impact other things, right? And more than anything, record keeping and reporting. And again, I would say, I've said before that testing is one of those things developers don't like. We hate doing it. I would say documentation might be right up there as well. We don't like writing comments. We don't like writing documentation. We like writing code is what we like doing. But documentation is important. We have to keep records and we have to report on what tests were done, how they passed, you know, and when they were run and stuff like that. That has to be part of the activities. Some simple advantages, right? Ultimately, if we have some type of software quality assurance mechanism in place, we won't have as many defects, right? Which means that our customers will have higher reliability. They'll have greater confidence in our ability to be able to perform, to be able to do the things that they've asked us to do. Big one, maintenance costs can be reduced. Software lasts for a long time. And if we're able to not have to spend as much money later to be able to maintain our software, that's much better. Okay. And again, overall life cycle cost of software is reduced because anything we don't have to spend later means that we can greatly reduce how much the total cost. Nothing comes for free. Nothing comes with advantages without also having some problems. Okay. One thing is oftentimes difficult to institute in small organizations. I mean, I'm sitting here, like I've told you guys in the previous set of slides about dividing up into development, testing team, and having all these other teams and stuff. If you have a very small organization, it can be hard to do that, right? It's hard to divide the group up into multiple teams. So you may not be able to do it as easily in a smaller organization. Oftentimes, it might represent some type of change, and change is hard, right? It's probably one of the hardest things to do is to tell people, yep, this is how you've always done it, and you need to do it differently now. You know, I've seen that in place. I've seen that multiple times, where that was probably the biggest hurdle, was getting some of usually the older programmers, but some of the programmers to accept that they needed to change the way they were doing things. Okay? And nothing comes for free. It's going to cost something on the front end. The idea is that in the long run, the total cost will be less if we apply some software quality measures, but it's going to cost more on the front end. And sometimes it's very difficult to say, this is something that, yes, it's going to cost more now, but it's not going to cost us as much in the future. Business people tend not to believe those kinds of statements. So it can be hard sometimes to be able to get that approval for something that's going to cost now. Okay. So we've seen this before. I think I've shown you this before, where the idea is that the cost of a defect found early on is much less than the cost of a defect found later on. Okay, so any defect that gets found way out here can be, as much as 15 to 70 times as much cost as if we were to find it way back here. Okay. Mostly because a lot of times with stuff like this, when we find a defect out here, to go fix it, we got to go back to here to fix it. But then when we get to here, we can't just test just the defect. We also have to test anything that the defect code may have touched, right? Other methods that called it, And so lots of more testing then has to be done in order to verify that the fix didn't cause more problems. If you've ever seen, there's a meme I've seen that talks about, I have 9 defects in my code. I fixed one. Now I have 16 defects in my code, right? And so basically the idea is sometimes fixing a problem will cause other problems, and it's not so much they cause other problems, they just make other problems more visible. Okay, so again, we want some kind of metric. We want more of a quantitative approach, so we can do that through the idea of the cost impact of software defects. And so the idea is here there are errors that may come in from the previous steps, right? And there are some errors that get passed through, right, just as is, and there's some errors that get amplified. So if they had been fixed back here, they would have cost a certain amount. If they get passed through to here, they get multiplied by a certain factor in order to generate. So they get multiplied by a certain factor because they'll cost more in this phase. All right, and then there might be some newly generated errors. So we have this idea of some 3 different numbers here. What is our efficiency for error detection in this phase, whatever phase we're in? And that should result in some general numbers of errors passed to the next step. Now, this is not what's the word I'm thinking of? We don't have an exact number. In other words, if we know there are 5 errors that come from the requirements phase, we're not saying, oh, we'll just let those pass through. No, what we do is as we work on projects, we keep track, okay? We keep track of what errors did we find out later on were actually generated during the requirements phase, even though they may have been found later in the testing phase, for example. And so we keep track of those so that we can keep this general average. So we'll have this average of the number of errors based on the size of the project that have been generally generated by us in these previous phases. And then as we keep up with those counts and keep up with those statistics, we can become better at predicting what type of problems we may encounter in the next one. And hopefully we're getting better. Hopefully knowing what we have done in the past will help us get better in the future. Okay. So an example might be something like this. So we have this preliminary design that's going to generate 10 errors. Now, we unfortunately are not good at detecting errors in preliminary design. So they just all get passed through. So they all just get generated. So now we have 10 errors that 6 of them are going to get passed through, but 4 of them become a bigger deal in the detailed design. And there's an amplification factor of 1.5. So now that means 6, okay, and detailed design generates 25 more. So if we add that up, 6 plus 25 gives us 37. And just like preliminary design, we're not very good at detecting errors apparently. So then those get all put out over here. So 37, all 37 of them get put over here. Now, 10 of those are just going to get passed through. And we, on average, 27 of them resulted in get amplified by the code and unit testing phase. So and there's an amplification factor that we have figured out ends up being about 3. And 25 on average got generated during the code and unit testing. Now, again, this is just based on statistics of projects that we've done in the past. This is not saying this is what we expect to happen, because again, if we expected errors, we would account for them in advance, right? This is about what we've done in the past. So when we add these numbers up, we get 116, but fortunately, we have shown that a number of times we were able to catch, some of those errors. Now, maybe it wasn't 100%, but we got 80% went through, but we did catch 20, so that's good. So what ends up happening is 80% of these end up moving on to integration testing. And when we move to integration testing, we follow the numbers. This should be true. Like, you should not be able to generate new problems once you are out of the coding phase, right? Because you're done making the software, so there shouldn't be any more problems, right? So 94, they all get passed through, but we caught 50% of them, so that becomes 47. 47, they get all passed through we able to catch 50% of them in validation testing. System testing, we got 24, 50% of them we caught, so 12. And latent errors, what latent errors mean are those are the ones that unfortunately made it out to the software that the customer saw. Okay, so again, these 12 errors would represent like that where Windows had to patch something, or where Apple had to patch something in order to make it work correctly. Those are errors found by customers and reported to those companies. Okay. There's some review checklist items. I'll go ahead and read through those. We won't go through those here today, but this is just some ideas of some of the things that you want to make sure that as you get through these different phases, okay, are we good? Are we good? So before we move on, make sure that these things are checked off. So I'm gonna go ahead and move on past the review checklist stuff because I want you to take care of that. And yeah, read through the formal technical review slide as well. Let's see, because basically the idea here is you have a review of the different stuff, of the technical stuff, of the design or the code, or whatever phase you're in. They will have a meeting. Everyone will need to sign off on it for us to be able to move forward. And there's a few different results that can happen. Is we can have a formal technical review that accepts the product without any further modification. It's perfect. It's great. Let's send it on, right? Or at least not perfect, but at least as good as we can get it. Okay, we can say reject the product. No, there's too many major errors. We are not ready for this to be sent out. If we sent this out right now, the customer would get very mad at us. So we need to go back to the drawing board and review after your corrections are made. Okay. We can accept the product provisionally. Basically, the idea is if there's some small issues that we see, we can suggest to the person in charge that those corrections must be made, but they're not so major that we need to have another review at some later date to make sure that corrections were made. Okay. All right. So that's basically, we want to get this or this as much as possible, as you would expect. I mean, you want to get accepted as much as possible. And again, we don't know for sure that it's perfect. We don't know that there's not some latent errors that we can't see, but this is, as far as we can tell, this is ready to go. Okay. All right. So software reliability is just the idea of probability of failure-free operation. So there may be some latent problems that we don't think will impact the system, that we don't think will be a problem. But basically, sometimes there's a trade-off that we have to do in order to either fix the problem, but it may be more costly than it's worth to fix it right now, and we might need to say we'll fix this in a future build. But this could be in a situation where it's like we don't think this will happen. It's such a rare occurrence that it's probably not going to be a problem, right? That could be something that we do in order to get things out on time or under budget, or something like that. Now, I will say that we have to be very careful with if we do stuff like that, because there was a story of in America there was a story of a car manufacturer. I believe it was the Ford Pinto, that they had determined that the car, if it was involved in an accident in a certain way, that the car would like catch on fire or something. Like it was like some crazy thing would happen, like something about the way the gas tank was designed. And it's a very interesting story. But basically, the engineers discovered this problem, and the business people took a look at the situation. They brought in some mathematicians and statisticians and what have you, and determined that the likelihood of that happening and the likelihood that if it happened that someone would die, and if those deaths resulted in lawsuits and they had to pay for the lawsuits. Okay, so they basically did this whole math calculation to figure out how much that cost might be. Right? And then they did on the other side, it said, okay, what's the cost of recalling all of the cars, getting them back here, fixing the problem, and then sending them back out? And they determined that the cost was greater than the cost was greater for the recall than it would be for all the lawsuits. Well, as you know, what would happen? Somebody did get into an accident. Somebody did either get seriously injured or died. I don't remember. And that resulted in a set of lawsuits against the company. And during the lawsuit, it was discovered that they knew about this problem. They knew that it could potentially kill someone, and they chose not to fix it. And so, of course, that resulted in a huge amount of loss of money. And I don't remember, maybe even some people lost their jobs over it or even went to jail. But basically, the court decided that you could not put a value on a human life, right? And so we have to make sure that when we're doing these calculations that we're not, risking people's lives in the process, right? So
do you remember when was the time of these events?
Oh, I want to say it was in the 70s. It was before you were born, I'm sure. It was before I was born. So
Yeah.
I can look it up. I'll look it up because it's an interesting story. I learned about it I learned about it when I was in university, over 20 years ago, in my ethics class that I had to take. So I'll try to find maybe it's probably on Wikipedia, and I'll send it out to.
Well, thank you. I think it was one of the best examples about this topic. Thank you for that.
Sure. I'll send it out to you guys because it's very interesting. It's so important that we don't just look at the cost in terms of dollars and cents or lira and kurush, whatever you want to use. But really that you cannot put a value on a human life, right? So, okay. So there is some, subset when we talk about this IO mapping is what we're saying is, okay, when we have a set of inputs, we should get a set of outputs. Right? So what outputs are mapped to what inputs? And we can get some problematic outputs and what inputs are going to cause those and what this whole idea of calculating the problems is what we may do is for those set of inputs that cause problems, we might say, that's going to happen so infrequently. That's going to happen so just rarely that it's really not worth fixing right now, that we can go ahead and send the software on. And so be part of our software quality review. All right. So we also want to have this call where a failure corresponds to an erroneous or unexpected behavior, and it's observed by a user. So that's a failure. A failure is when a user experiences a problem. Okay, a fault, and this is where we get the differences between a fault and a failure. A fault is something, or a defect. A fault is something that can cause a failure to occur. Okay, now, if we have faults, that doesn't mean that we're definitely going to have a failure, right? So let's say, going back to my example from before, the dollar sign. All right, really what the problem was that field, it expected a number, but he didn't force it to be a number. You could type anything in there. You could type a word in there and click submit, and you would get the same error, all right? But I'm sure that our company could have looked at that situation and said, what's the likelihood that a user is going to put a word in there? What's the likelihood that they're going to type in the words 100 or something like that? Well, that's unlikely. So they might have thought, yeah, that's a fault. That's a problem in the code, but it's unlikely to generate it's unlikely to generate a failure. The problem was in that situation, I would say, and I think we wisely agreed, the company, when we decided what to do with it, agreed that it actually was a pretty high likelihood of something like that happening, because what a user might do is copy their value that they're looking for from some other source, like a website or from some other text document that they had. They might copy the value and paste it into the field, and that copy and paste might include a $sign or some other special character. And so we decided that the likelihood of something like that happening was high, and so therefore that fault could generate a failure, and that was something we wanted to avoid. So the main thing is, what we want to get rid of is we want to get rid of failures. That doesn't mean we have to get rid of faults. But we do know that a fault can cause a failure. A failure comes from a fault. Okay. Yeah, take a look at this reliability improvements, because we don't necessarily, it's not a one-to-one ratio. A removal of so many faults doesn't necessarily mean an automatic same percentage improvement of reliability. All right, so in one situation, removing 60% of faults resulted in only a 3% improvement in reliability, which meant 3% fewer failures. Okay. Again, removing faults with the most serious consequences is the primary objective, human life, right? So if some fault could result in a failure that could, cost somebody their life or or even cause major injury, then that would be something that we would want to fix, even if it's highly unlikely to happen. Okay. All right, so I did also include this 5A that I want to go over as well, and I'm hoping that we'll still have some time to have a brief discussion before I have to end. Okay. So this is just some of the specifications for some of the documentation and stuff like that. So a requirements document is something that we should have. We should have some type of requirements documentation so that we know what our system is going to be. What is its purpose? What is it going to do? It doesn't have to be like a Word document or a PDF with like certain formatting and stuff like that. In fact, if you've ever heard of SysML, it's an offshoot of UML. If you know what UML, Unified Modeling Language. So SysML is Systems Modeling Language. And one of the possible, what's it called? One of the possible models you can create is a requirements model in the SysML. So you can actually model your requirements instead of writing them up in a documentation format. So there's many types of forms that a requirements document can take. But it is very important for us to understand what is the expectation of what our software is going to be and do. Okay? So we want it to be testable, so we can find bugs before the software is even developed. Remember, what we would love to do, what we want to be able to do is find defects before especially those that might cause failures, or especially those that are likely to cause failures. We want to find them early in the process instead of late. Okay? Again, some of the testing fundamentals, black box testing, right, is again, we're outside of the box, and we're trying to just test what we can't see. We talked through about white box or clear box testing, and also, there's also some static testing that may go on, testing software without running it, where we could look through the code. Sometimes we might be able to just look through some few lines of code and just look at it and know that it's not going to do what it's supposed to do, and that could be the best kind. That could be some of the quickest to fix kind of bugs. We'll have dynamic testing. It's called running the program. Right. Again, testing specification. how are we going to go about testing? How much black box testing? How much white box testing? How much static? How much dynamic testing are we going to do? Right? Again, the goal is to find bugs early so that we don't have to deal with them later. Okay. All right, so we're going to have a high-level review. So we're going to stand back and just kind of view it. Don't look at individual units or code, but just kind of a high level. Okay, what is it we're trying to do? Right. This is probably one of the harder things for developers to do because we think like technical people, and many of our customers don't. In fact, I bet most of you probably have some story, as I do, involving a family member who did not really understand how computers work, and they asked you, and it's like there's a joke, about like you're trying to walk your mom through how to do something, and you tell her click the start button, and she says, "But I'm trying to shut it down. Why do I need to start?" Or just different things like that, where where we don't think like non-technical people do, right? And so sometimes we need to be able to pretend to be the customer to figure out, okay, what is it that they would do that could break this thing? Okay. Remember, one of the purposes of testing, probably the primary purpose of testing, is not to prove that software works, or any system, or anything for that matter. It's not to prove that it works. It's trying to find places where it doesn't. All right, it's trying to find places where there are problems. That's what testing is all about. I mean, even in today with the COVID pandemic, right? The purpose of testing is not to prove that a certain population is healthy. It's trying to find out which people in the population are not and be able to get them the help that they need, right? And so, anytime I hear somebody talk about we need to test less because the numbers are going up, I think that's the exact opposite attitude that we should have, because the whole purpose of testing is to find out where the cases are so that we can get people the help that they need. All right. Again, research existing some standards and guidelines. Why do they exist? What are some of the terminology? What are some of the industrial and governmental requirements? Again, the last thing you want to have is to have a good working system that you find out late that it doesn't conform to some government requirement, and you have to go back and fix a bunch of stuff that you weren't planning on. Okay. Yeah. So you want to review and test software. You want to use it. You want to make sure that it's efficient. Let's see. I feel like there's something that didn't get over there. Okay. All right, and then there's the low-level specification where we get down into the minutia, the small parts of the system. All right. All right. One of the things when you do the specification technology, one of the things you want to avoid is problem words like always or never, or or absolute style words, or obviously sometimes. Usually we want to have a quantitative understanding of what it means. So you don't say most of the time, right? You don't want to say no. You don't want to say that something works most of the time. You'll see different important systems will talk about their uptime, right? And their uptime will be something like 99%. And what that means is that they're not always up. They're acknowledging that their servers, that their website, whatever, is not going to always be up. But they're guaranteeing that at the very most, it will be down 1% of the time, right? And so that's something that's testable. Most of the time is not testable, right? Because we don't know what most of the time means, right? And we can always say that, well, most of the time, well, this, I said most of the time, and 50%, that's most, right? No, okay. You need to have a way to test whatever your requirements are, okay, whatever your requirements for testing are. Again, good, fast, cheap, efficient. None of these are quantifiable words. What does cheap mean? Well, cheap to me might mean something totally different to somebody else. Well, what does fast mean? Well, again, fast to me might mean something totally different to someone else. We need to know what is fast. Okay, how fast are you talking about? Are you saying this result will be given to me in half of a second, or are we saying this result will be given to me in 3 seconds? Because those are two different amounts of time, right? But they're both testable. We can say, yes, it got back to me in less than 3 seconds. We tested it, it worked. Okay. All right. All right, so this is just some words you want to avoid, some thoughts you want to avoid in your testing, okay? All right, so you want to make sure it's testable. You want to make sure that it is able to, we can generate pass-fail requirements for being able to make sure that the software does what it's supposed to do, right? For example, this would be like test or use cases might be another word we would use for these. For example, the user will do such and such, and the results will be this. The user will click this button, and this will happen as a result. That kind of stuff. Okay. Again, all aspects of the scenarios must be covered as far as we know. Okay. Now, again, so we have a subjective process, is not step by step. All right, our higher level review, so we don't want a very subjective process, right? We want a high level review to be able to get any oversights or omissions. So we kind of take this high level, what we maybe call a bird's eye view of the system to be able to see, do we forget anything? Did we miss anything on how the system is supposed to work as a whole? Then we go into the low level to make sure all the details are well defined. And then we have a good idea of how to develop the testing, the test cases, the test suite from that. Okay. All right, so that ends this set of slides. Again, what I want to do for future weeks is I'm going to upload the slides in advance of the lecture. So Monday, you should see these slides. In fact, I should probably go ahead and put a reminder to make sure that I upload them. Okay. I'll do that after we click close on this. And so then I would want you to read over those in advance of the lecture and then come with some questions about what you saw in those. Yeah, and Aiden, you had messaged asking about an extension. What we can do is we can make it 2 weeks from today. Okay, so let's go ahead and do, the deadline will be 2 weeks from today for you to have that paper to me. And I'll go ahead and post that assignment here. I'll do that as soon as this is closed out in a few minutes. Okay. Sure. All right, so are there any comments or questions about what we talked about here today with kind of the software quality overview, software quality assurance overview, and kind of how to start testing and whatnot?
Actually, can I ask a question about homework?
Sure.
I already submitted it. Should I change it or just left it like this?
Let me take a look. Oh, what did I put it up here? I didn't know I'd put it up there already. Oh, you're talking about the term paper. The only thing I put up there was the term paper.
I think he uploaded into the files in our general team.
Yeah, exactly.
As named as summary.
Let me see. Take a look and see if I got it here. Did you put it into a folder? I'm not seeing it.
No.
Is it under the readings folder? No, I don't see it in the readings folder.
It's under general tab and files.
Oh, maybe under here. Oh, I see. Okay, I found the files tab. Under class materials? Yeah, Which folder did you put it in? Just under. Oh, I see. I see. Okay, I see. A summary. Wow, how did that get there? Oh, you know what? That folder, I see it now. That folder, the files thing, it's not synced to my local computer. Okay, that's why it's not on my computer. Interesting. Okay, yeah, no, if you've already uploaded it, that's fine. If you just did it early. What I will do is I will open up an assignment, though, for you to be able to submit it through there. So I think that would be a lot easier for me to keep track of things. So if you can just put it into there whenever that assignment becomes available, that would be better, I think. Okay.
Okay.
Sorry for the confusion on that. I meant to. I thought I'd already put that assignment up. I thought I made it. I'll do that as soon as we get off the call here today. Okay. Well, if there's anything else that you guys want to talk about the quality assurance overview, let me just go ahead and repeat what I want you guys to do, what I would like you to do before next class. In addition to go ahead and start reading those papers if you haven't already, is go ahead and familiarize yourself with the JUnit test cases and how to run those on a piece of Java code. There's some. What I can do is I can give you some. I can write up an example one and upload that into the class materials folder for you to kind of see a very simple example of how to do a JUnit test case. Okay, so we can do that. I can have that done by Monday. Yeah. But I do want you to understand how to run JUnit tests on a Java file so that you can be ready for that assignment when we do that later this semester. Okay. And also
Okay.
make sure you're looking up research papers for the term paper, because I'm looking forward to you guys presenting.
About that, are we going to give a first phase presentation about our paper idea or something like that? Are you
No,
planning?
just give me what I would like is, and I didn't do this in stages. I should have done this in stages. What I would like would be within the next, couple weeks, 2 weeks, 3 weeks, something like that, is for you to tell me what you want your topic to be. Okay. What focus you're trying to do. So, like, for example, my topic in the example presentation I sent you was the cultural effects on software quality. So, you could just look at how a particular software process impacts the software quality. It doesn't have to. I believe I said it could be in the areas of software process, software engineering, or software quality assurance, I believe is what I have on there. So yeah, so go ahead and start looking at papers on that, on whatever you want your topic to be, but make sure to let me know what your topic is going to be so that I can approve that and we can have, so that we can go ahead and get that going. Okay, thank you very much. Sure. Software process or software quality assurance, that's what it is. All right. No more questions? No more comments? All right. Well, I'll see you guys. Look out for the slides to be on Monday uploaded, and I'll see you next week otherwise. All right. Have a good weekend. You too. Thank you very much. Goodbye.